Welcome, everyone. Very pleased to have you with us here today for This Is CDR. This Is CDR is an online event series presented by OpenAir to explore the wide range of carbon dioxide removal solutions currently being researched, developed, deployed, and contextualize them for policy proposals we have under development for New York and other states and localities. Everyone, please feel free to introduce yourself in the chat and tell us where you're zooming in from. I'm Toby Bryce, based in Brooklyn, New York, and I work on CDR policy advocacy with OpenAir. Just some quick background on OpenAir. We are a distributed volunteer network dedicated to the advancement of carbon dioxide removal solutions essential to solving the climate crisis. Our growing global community collaborates on shared open source missions in the areas of policy advocacy and research and development. There should be some links into the chat to our website where you can learn more about what we do. And on the website, there is a link to join our group. You can kind of fill out the form and sign up, and many things that we can work on together. Quick background on carbon dioxide removal. Carbon dioxide removal comprise activities that remove CO2 from the atmosphere and durably store it in geological, terrestrial, or ocean reservoirs or in long-lived products. When you're considering CDR as we are today and with the series, it's essential first and foremost to emphasize that CDR is not in any way an alternative to reducing emissions. We must reduce global emissions and decarbonize our economy as quickly and as completely as possible, full stop. That said, every credible climate forecast, including in very stark terms, the most recent IPCC assessment report show that CDR will be required at gigaton scale, that's billions of tons per year by mid-century, to remove the tremendous excess of anthropogenic carbon dioxide already in the atmosphere, and also to counteract those emissions that are difficult and or inequitable to abate. If you're new to CDR, there's an icon right here, the Carbon Dioxide Removal Primer, which is a great textbook, basically, that kind of outlines all of CDR, and it's really a fantastic resource. The past episodes of This Is CDR are also a great place to start. We've done 12 of them now, and those links are available online on OpenAir's YouTube channel. And I'm also going to add one other resource that was recently published on Friday when the Department of Energy Fossil Energy and Carbon Management Group, led by Dr. Jennifer Wilcox, announced the Earthshot for CDR, which is super, super exciting. And the resources that went along with that announcement, I think we can put a link to those in the chat as well. Those are just really comprehensive and tremendous. And it's also a super exciting initiative that I think will really provide a lot of support to the overall sector. Now, please meet my colleague, Megha, who is going to introduce our speaker today.
Hi, everyone. I'm Megha Raghavan, usually based in London, and I also work on OpenAir's CDR policy advocacy team with a particular interest in the legislative policy opportunity for California, where I'm from. This week, we're very happy to welcome Peter Reinhardt to tell us about Charm Industrial's industry-leading and highly permanent carbon removal process, which generates bio-oil via fast pyrolysis and pumps it for sequestration deep underground. Just as usual, the housekeeping notes. So our format will be about a 15 to 20-minute presentation, followed by a few prepared questions, and then we'll do moderated audience Q&A. So please type any questions you might have for Peter into Zoom's Q&A box as we go along. Note that that's separate from the chat box. The event is being recorded, so we'll send that video link out to everyone who registered, and we'll also post it to OpenAir's website and to our YouTube channel. We will also be live tweeting today's event. We'll put our Twitter link in the chat, and please follow along. If you do tweet, the event hashtag is #ThisIsCDR. Now for the main event. Peter Reinhardt is the CEO and co-founder at Charm Industrial, where they're developing novel carbon removal and renewable industrial syngas technology. He is also the CEO and co-founder at Segment, a SaaS customer data platform, which grew to 600 people before it was acquired by Twilio in 2020. He previously studied aerospace engineering at MIT. Peter, over to you.
Awesome. Thank you, Megha. Well, excited to be here today. I am calling you, I apologize, it's dark here in Glasgow. I'm here for COP26, and it's been an interesting couple of days of CDR discussions. So I'll share some slides and dive into Charm. So at a high level, what Charm is doing is putting oil back underground. And if that sounds a little ridiculous, it is a little odd. Key thing to understand is that the oil that we're putting back underground is very low energy. So we're really putting the carbon back underground in the form of bio-oil. So I think something that's important to understand is that carbon offsets have historically been dominated by nature-based offsets. The market is about $500 million a year as companies and individuals purchase these nature offsets. And these voluntary markets are dominated by very, very low priced nature-based offsets. And when I originally started trying to purchase these offsets for Segment back in the day, I was a little disturbed actually by what seemed like kind of a low quality bar for these offsets. And in fact, that's what's been borne out. So the latest research from Berkeley, Stanford, Oxford, Carbon Plan has shown that about 85% of these offsets that are sold today are not additional. In other words, the project would have happened regardless of whether you purchase the offsets. It's being done for some other reason, often health or something else, biodiversity, etc. And then another 35 to 82% of these offsets have significant leakage. And then of course the permanence is extremely short. And so if you were to look at these existing nature-based offsets on a pure just carbon tonnage basis, none of these co-benefits, then actually the price for these offsets is not in the $10 to $20 range that it might be on average, but actually up in the hundreds of dollars on a true carbon permanent basis. So that sort of scrutiny is now coming to light. There's a lot of articles been published about this in Bloomberg and Tech Review and so on, as well as the research from Berkeley. But this is what's driving the interest in engineered removals, specifically the measurability and permanence that come with an engineered solution. And what you're really looking for is certainty on the CO2 impact. If you engineer this, then you can measure it. You can measure the amount of CO2 flowing through the pipe or other material flowing through a pipe. And you understand the permanence a lot better because you're often taking it out of the biosphere, putting it deep into the geosphere or sometimes oceans where maybe understand chemically in detail what's going on. But the point is to get it into a system where it's measurable and highly permanent. You know, there's challenges with direct air capture, there's challenges with every one of these methods. The main challenge that we see today of why engineered renewables haven't taken off is just the direct air capture can be very expensive. So if you look at bio-oil sequestration, it's a new engineered pathway. It's about 18 months old. My co-founder Sean invented it back in April or March of 2020. And the pathway here is that we take cellulosic biomass waste, so agricultural residue, corn stover in particular, but also sugarcane bagasse, rice straw, wheat straw, as well as timber residue, so tree tops and branches. We take that agricultural residue, cellulose that has already captured CO2 out of the atmosphere by plants, and we then liquefy it via a process called fast-pyrolysis. So we take the biomass, sort of push the cellulose out of equilibrium into this liquid form, very rich in carbon, not particularly energy rich. It's not really an oil, it's 30% water, 25% acetic acid. So we take that carbon soup, if you will, and we pump it deep underground into these sedimentary geological formations, often old oil and gas reservoirs. And that permanently stores the bio-oil, partly because as you inject the bio-oil, it actually sinks in the formation. And so it's denser than the brine that it's injected into. So it sinks, and then what we're finding from core sample tests at the surface is that it tends to solidify within just a day or two. So very quickly, you have a solid carbon formation underground from what was plants growing on the surface. So a few reactions we often get to this, like, wait, you're crazy. Why don't you just inject normal oil? Why do you need to do this with plants? Well, if we're just extracting oil from the ground, moving it and putting it back underground somewhere else, on a net basis, all we've done is emit some CO2 for whatever the infrastructure was to do that movement. But if it's coming from plants, the plants are actually capturing it out of the atmosphere. And so we're getting a net removal there. Another common question is, why not use bio-oil as fuel? There are a number of folks who are successfully using bio-oil as fuel, but there's also a very long history here of that not being successful. So many bankrupt attempts over the last 40 years. I think one company that may actually be on this call, BTG-BTL, is actually maybe starting to succeed at turning it into a fuel in Europe, but it really doesn't have that much energy content, and so it can only be blended in a small proportion. It also has this tendency to solidify that I mentioned before, which is a feature for sequestration. It's a bit of a bug when it's a fuel. And the way that we look at it is just that the bio-oil carbon value is higher than its energy value. So is there enough biomass to make a meaningful dent in the amount of removal that we need? Well, the newest IPCC models that came out this summer suggest that we'll need somewhere between 5 and 20 gigatons a year of removal by 2050. So if you look globally at the sort of accessible biomass, so on land, reasonably dense, etc., you get to about 10 to 20 gigatons a year of biomass, about a gigaton a year in the United States, about 200 megatons just of corn stover in the United States, sustainably sourced. And so in other words, then that biomass converts into CO2 removals on about a 1-to-1 basis when you sort of do all the chemistry. So in other words, there kind of is enough biomass here to make a really meaningful dent. If not cover all of it, that's probably unlikely that we'll reach all of this biomass, but a really meaningful dent for sure in the amount of removals that we need. Now, a few questions that often come about biomass. Isn't biomass already used? You do need to leave some biomass on the field. So when we talk about corn stover, it's really important actually that you leave some corn stover on the field to prevent soil erosion, to keep soil carbon high, etc. You can leave about 50% and remove 50% sustainably. Now, there are many other proposed use cases for cellulosic residue, but relatively few that are actually in production, at least in the United States, more in Europe, but less so in the United States. So, there's 200 million tons of unused corn stover in the United States every year. In California, we have enormous problems with excess forest residue. Cal Fire, Cal Recycle, all of these government agencies that are trying to pull forest residue out before it lights on fire or pull timber slash out. It's many megatons, tens, maybe even hundreds of megatons when you start going all the way up the West Coast and into Canada. Pretty quickly get to a gigaton of completely unused biomass that's just rotting every year in North America. Another common question is, shouldn't we just use biomass for energy? There's a couple different ways of looking at this. One, if you look at it from an economic perspective, basically all the biomass energy companies in California have failed despite subsidies and despite other things. It's not economical to transport biomass over long distances, and biomass for energy has not been competitive with solar. So that's one way to look at it. Another way to look at it is if you were to take natural gas and replace it with biomass, you're going to reduce emissions by some amount. If instead you burn the natural gas, but instead put the biomass underground via removal, how much gets removed? Well, it turns out you actually mitigate more CO2 by putting it underground via the sequestration process than you would mitigate by burning it for energy. So again, the carbon value of biomass and bio-oil is higher than its energy value. Another key part of the CHARM model here is we're developing small mobile bio-oil plants to sort of keep biomass supply demand in check. Historically, people have built very, very large plants. So this is a picture of Abengoa-Hugoton, which is a 1,000 ton per day cellulosic ethanol plant in southwestern Kansas. Their $65 per ton biomass projections became $125 a ton in reality as they bent the supply demand curve and sort of saturated the local market. So instead, we're building very small units, trailable 40-foot shipping containers, 10 tons per day, so 100 times smaller. And this allows us to push it to the field edge, mobile, move it all around North America, searching for the lowest cost biomass. And this really sort of fundamentally changes the cost structure. We can inject into a number of different formations: class 1 wells, class 3 wells, class 5 wells in the United States. These are industrial waste disposal wells as class 1. We can also fill in old solution mining caverns or class 5 salt caverns to restabilize them at sort of end of life. So a lot of options for injection, and broadly speaking, sequestration of bio-oil is dramatically easier than sequestration of CO2, partly because you have, again, it sinks information and solidifies. So you have a lot less constraints than with CO2, where you need lots of salt domes and other things to contain it. So on a life cycle basis, if you have 1 ton of biomass, that is 1.65 tons of CO2 that was absorbed to make that 1 dry ton of biomass. We do re-emit some of that in consuming some of the biomass for heat energy to drive the pyrolysis process. And then there's a small fraction that's used for production, transport, and injection, and you get a net CO2 reduction or removal. And this, over time, as we improve the efficiency of the machine, this will grow, but this is sort of roughly the life cycle as it stands today. Over the last 18 months, we've passed a number of sort of rigorous scientific validation behind in sort of the analysis cycles that go on with scientists behind Stripe, behind Microsoft, behind Shopify, as well as the folks at Carbon Plan. It's been awesome to have them really dig in and sort of validate what my co-founder Sean came up with. We also signed contracts with all of them, and they've all since renewed. Our first demonstration of this sort of pathway was 10 months after initial invention in January of this year. This is my co-founder Sean at a rail translate facility in Oklahoma, a rail yard worker that requested a CHARM sticker for his hard hat, which is pretty awesome. and the injection well that we've been working at in Oklahoma. The first demo is 25% lower cost than direct air capture. And since then, we've delivered a lot. Actually, this deck is slightly out of date. We've delivered over 5,000 tons to date. We just announced the 5,000 ton milestone last month, including delivering both Stripe and Shopify's contracts and Microsoft's contracts all ahead of time. So super proud of the progress that we've made in the last year. It's amazing that Climeworks has launched Orca. Super excited about that. I was just talking with Christoph at Climeworks earlier today. I think very much want to sort of be in a race with them to figure out, how as an industry we can accelerate capacity building. But also proud of what we've done over the last year at Charm. We've removed about 5,000 tons, and that's about 80–90% of permanent carbon removals to date. And we are planning to drive a declining cost curve from a current $600 a ton down to about $50 a ton. And the key at the beginning is really driving down the cost of the capital equipment, so driving down the cost of the pyrolyzer. And the main things that drive that are the labor associated. Right now, it's hand built by amazing mechanical engineers in San Francisco, and over time, obviously, it should be built by technicians and manufacturing lines. Dramatic simplification of the machine that will certainly happen over time. This machine is very complicated right now. Lower cost of capital, currently funded by venture capital at 40% kind of IRR. At scale, that should be 5 to 8% kind of debt rates, and lifetime. So currently, we assume about a 6-month operating time, which is crazy low. A normal pyrolyzer might operate for 20 years. We're planning for maybe 7 years at the tail end of this model. So the capital costs come down dramatically, and you can see the green costs for biomass start to dominate over time. And so there's things that we're working on to reduce the cost of biomass now going forward. So with that, maybe I will pause and switch over to Q&A, sort of a hopefully a high-level introduction to what we're doing at Charm.
That was fantastic. Thank you, Peter. Really great detailed presentation. And also congratulations on your delivery of the thousands of tons. I believe that you have delivered more CDR than any other company, permanent CDR, and any other company in the world. So that's fantastic.
That's a belief. We'd love to be wrong. If other folks have put stuff underground, please let us know and we'll update the chart.
Let's get more. What starting back with the sort of Charm origin story, you explained that you kind of got into it by trying to buy offsets for your previous company. From the invention, was the process that you're using now, is that the specific process that was kind of the initial invention, or did the idea evolve a little bit as you started to think about it and work on it?
It evolved quite a bit. So we started looking at my own journey started with offsets and sort of going down the rabbit hole of how to get to permanent carbon removals that were highly additional, no leakage, et cetera. And we eventually started to sort of have an interest both in carbon removals as well as industrial decarbonization. And we found that biomass gasification was an interesting route. So we were specifically looking at large central biomass gasification facilities that would be co-located with consumers of syngas. So refineries, ammonia production, steel, et cetera. The problem that we ran into was that the logistics of moving around biomass are very poor. So you just can't move biomass very far, maybe 50 kilometers. And so that's a challenge, because you literally can't get enough biomass for these big industrial facilities. And so the key insight that my co-founder Sean had was that if we split our gasifier into 2 machines, we would actually sort of do a half-ass thing first, where we converted the biomass into a liquid, and then the liquid was very transportable. And so this resolved a bunch of logistics issues. So that was the sort of first insight that sort of started our pivot maybe 2 years ago. And then the second, and now you're talking about in one of these big facilities, rather than bringing in 300 trucks a day of biomass, you're talking about bringing in 30 rail cars a day of bio oil. Totally different calculation. The second insight that he had was, hey, we need to come down the cost curve. So somehow we have to be able to somehow we have to produce bio oil that's more valuable in order to start building these pyrolyzers and get up the scale, get down the cost curve in order to get to these industrial use cases. And at some point he was trying to figure out how to dispose of some bio oil. And one of the options that came up was actually disposing it in a well. in industrial waste disposal well. And then it sort of clicked for him, like, oh shit, like, wouldn't that be a permanent carbon removal? And so the more we looked into it, the better it got. And so that became actually our initial market. So we'll start with carbon removals, voluntary, then we'll go to regulatory carbon removals. Voluntary is sort of the Tesla Roadster, regulatory is sort of the Model S. The Model 3 will still be industrial syngas applications mediated by biooil.
Cool. Couple questions. Can you just recap your regarding your the efficiency of your process? The 0.76 number, does that mean that you are currently at a 76% carbon efficiency process, or is it what is the denominator?
It's about half. It's about
okay,
half.
So 50%.
About 50%. Yeah. As first of kind, we'll get there.
And then
we'll get better.
Yeah. And what do you feel like is the theoretical maximum efficiency of the process?
That's a good question. I don't know that off the top of my head. I would assume somewhere around 70 or 80% is probably close. Is probably close to the theoretical maximum, but
okay.
I don't know if it's actually possible to get there.
And then per ton, can you just recap so per ton of dried waste biomass, how does that translate into bio-oil and then the actual CO2 equivalent sequestration?
So a single pyrolyzer processes 10 tons per day of biomass and produces about 5 tons per day of bio-oil, which is on a net removal basis about 7.5 tons of CO2 equivalent.
Got it.
Give or take.
Okay. And then on the waste biomass slide, can you recap those numbers again? The global, and that you said the slide said biomass, but you're referring to waste biomass, right?
Yeah, that's right. We're looking at both agricultural residues and forestry residues.
And the total global for that is what?
It's really hard to tell. Yeah. We know that. So let's start in North America. The DOE has produced the 1 billion ton report, and the two biggest components of that are corn stover and forestry. So you add up just corn stover and forestry and pretty quickly get to 0.5 gigaton in the United States. If you extend that to Canada, you start getting up pretty close to this 1 billion ton, even with just a couple of these basic feedstocks.
Uh-huh.
So in North America, then you're looking at about 1 billion tons, give or take, of residues. And then if you look at sort of like arable land area and sort of estimate then across the continents, you get up to about 10 to 20 gigatons across the world.
And again, the sequestration amount is 75% of that, so of carbon. So
currently it really will get to 1-to-1 very easily. So yeah, so I would just go 1-to-1 of biomass tons equals CO2 removals.
Got it. And a lot of when I hear a lot of questions about charm, can you just I'm sure it's very complicated, but can you compare and contrast your pyrolysis process with the pyrolysis process that produces biochar, and then talk a little bit about the pros and cons of bio-oil versus biochar as a CDR solution?
Yeah, so broadly, pyrolysis can be tuned. You're going to get 3 outputs no matter what. You're going to get a solid output of char and ash. You're going to get a liquid output of bio-oil, or a condensable fraction of bio-oil, and you're going to get a non-condensable fraction of gas. And the question is, what do you do with each of those 3, and which one are you optimizing for? So if you want to optimize for gas, you go very hot. If you want to optimize for solid, you go low temperature, long time period. If you want to optimize for liquid, you go middling temperature very quickly. And so anyways, you can tweak the process. But so we sort of optimize for that middle pathway of very quickly heating the biomass and converting to a liquid as much as possible. But we do still have a gas stream, which we can use to power generators to create electricity for the whole system because it needs to run off grid. And we also have a solid stream, which contains all the ash and a bunch of nutrients, which needs to go back on the field. And that said, we don't sell the biochar, like the carbon that comes out in the char, it goes back on the field. We don't sell that as carbon removals, partly because we're not convinced that it has a high enough permanence, doesn't clear our permanence bar yet. The science might get there, in which case we're happy to sell it, maybe back sell the stuff that's been done, but we're not convinced enough of the permanence there yet.
Okay. And your bio-oil, is it technically an inorganic carbon or an organic carbon?
It's organic. Well, it's a mix. Bio-oil is is a whole bunch of stuff.
Okay.
It's like 30% water, 25% acetic acid, and then it's a mixture of phenols and sugars and aldehydes and ketones and esters and ethers, and you name it. So it kind of has everything in it, but it's definitely an organic carbon mixture.
Got it. One last question, and we have a large number of audience questions we're going to get to. It's actually a two-part question. Can you talk a little bit about, you had a slide about this a little bit, but specifically the marketplace for CDR and how you see it breaking out over the next decade. To date, I guess most of your volume has been through direct voluntary purchases with Stripe, Shopify, Microsoft. There are a number of early stage carbon offset marketplaces that are focused to varying degrees on permanent CDR. I think you recently invested in a UK-based company called Supercritical, and the incumbent in the space is maybe Patch, based in San Francisco, and there are several others. What role do you think that, or how do you see the market breaking out? And sort of one of the things that prompted this question was on one of the climate slacks, the North American commercial lead from a fairly prominent CDR company was complaining about all of the repetitive RFPs that they had to fill out. And, ideally, that's not a super efficient process to be filling out completing an RFP for every deal. So how do you see that playing out, or maybe over the next decade?
Yeah, I'd say to date, obviously the first three purchases were Stripe, Shopify, Microsoft, and those had sort of extensive RFP processes. I think what we're seeing now is other technology software companies sort of understanding that carbon dioxide removal is going to be really important, that they need to pay a premium for it, that they should help come down the cost curve, et cetera. And so other tech companies have followed in their footsteps and are now continuing to lead the charge towards bringing things down the cost curve. I think as we get to beyond sort of that initial part of the ecosystem and these early adopters, the role of consultants, advisors is really important. So folks like Watershed and Supercritical and Anthesis and so on, because people don't have time to. Stripe, Microsoft, Shopify have gone and invested big time in creating programs to sort of lead the way here. Not everyone is going to do that. And so having some repeatability in the sort of expertise and products that can be built in these companies is, I think, important. And we're seeing a good amount of sort of flow through those now. So I think a marketplace is a long ways away. That sort of implies commodity prices and other things that we're not even close to by any shape or any kind of imagination. But I do think that we'll start to see more and more of the sort of resellers and advisors start to build into their portfolios for companies carbon removals. I think the Science Based Target Initiative also just changed their guidance so that it now includes sort of guidelines around how to include carbon removals in an offset purchase. So anyways, I think that sort of set of consultants and products and advisors is probably where the bulk of CDR is going to get recommended or sort of really purchased over the next 5 years at least.
Okay. So you don't see like a true programmatic marketplace emerging in the immediate future. It's going to be human element.
Yeah, there's too much variation in price and quality and like, these nuances of these sort of secondary characteristics. It's not a commodity yet.
Yeah. Got it. Okay. And as you know, that we at OpenAir are working on a state level carbon removal procurement policy that we're going to have some news on soon. Obviously 45Q and the California low carbon fuel standard are important compliance mechanisms and tax incentives. How would you see, like, if governments became a buyer of CDR, do you think how would you see that kind of helping to scale the marketplace?
Well, we need a lot more dollars flowing into CDR procurement. Like, you can kind of just run the math. And like, if we're gonna hit the targets that we need to, then by 2030, it's like, on the order of several $billion, per year needs to be purchased. So the question is, where is the several billion going to come from? It's probably not going to come from voluntary markets.
Right.
It could come from maybe government procurement, which is sort of like an interesting subset of voluntary, right? The government is sort of volunteering to make these purchases. Also interesting are the regulatory markets. Like, can the government create a market that forces companies to buy more? So some mixture of all three of those is going to have to get us to the full amount, I guess, eventually, but at least kind of 4 or 5 billion a year by 2030. So I think government procurement can play a really important part. in putting a significant amount of dollars to work in this area.
Got it. Great. Mega, do you want to hop on and start posing some of these audience questions we have?
Sure, we have quite a few. All right, let's start with a couple on just kind of some things that you've touched on already. So one thing you talked a little bit about was how your process compares to biochar and some of the others. Can you just talk a little bit about the life cycle analysis and how that compares to other biomass procedures like BECCS or anything else, and what are the pros and cons of the different ideas out there?
Yeah, so with BECCS, you basically are taking the energy out of the biomass and converting it all the way to CO2 and then pumping the CO2 underground.
Right.
And then with bio-oil, we're not really trying to extract the energy. We're just trying to extract the carbon into a different form of bio-oil before we put it underground. The trade-off is that BECCS hasn't really taken off because the bioenergy basically has negative value, right? Like you can't do it economically. It has to be done at a loss because solar is a cheaper form of energy, even renewable. So that basically forces you to pay for the electricity that you're producing with the CCS part, which is also not profitable for CO2 because of the monitoring and class 6 well and so on. So the whole, I would like BECCS to succeed, but the economics of it don't pencil right now.
Makes sense. And what about trying to use the bio-oil to produce chemicals or anything else? Is that viable as opposed to sequestration or fuel production?
It could be. We weren't able to find a pathway, but that doesn't mean that it's not. I think there are quite a few, over the last 10, 20 years, there have been quite a few pyrolysis companies that have focused on trying to find chemicals that can be produced, or like asphalt or barbecue sauce, like all kinds of things that people come up with to make from bio-oil. They haven't taken off. It doesn't mean they don't exist, but we're not aware of any. Okay.
There were a bunch of questions about kind of the details on the injection and how different options you could have with that. So one question was, does it make sense to try to remove the water before injection, or how does the water affect everything from the stability to the cost to everything else?
I think the water is like mostly irrelevant. When it gets downhole, it's going to mix with water anyways. So I guess it has a slight penalty on the transport cost, but separating it out is also expensive because you have a bunch of it is soluble, right? Like all the sugars and stuff are soluble. So separating it out is challenging. Not to say you can't do it, but I think it's sort of an expense that doesn't get you much in the way of value downstream.
Yeah, makes sense.
I should say for our use case of carbon removal, if you're going to try to make bio-oil into fuel, it's actually really important because the water is killing your energy content and heat properties and stuff like that.
Okay. We had a few questions about sort of, I guess, essentially environmental risk factors. So is there any risk of the carbon decomposing either into methane or other substances that could be released or into things that can like leak into the surrounding area?
Yeah, not to our understanding. So when I guess one thing to clarify is sort of how deep is this going? We are talking about, the first maybe 1,000 feet and even deeper sometimes can have aquifers that matter. So we're not talking about soil, we're not talking about the aquifers. The design of the well is constructed, we can get into this if you're interested, the design of the well is constructed such that confidently that you are injecting well below any aquifers into sedimentary layers that used to contain oil and gas, typically sedimentary rocks, but also these class 5 salt caverns or class 3 solution mines that are kind of end of life. Anyway, in any of these cases, you can be confident that you're not putting into aquifers. Also confident that we're not generating methane. That would be a big problem since methane is such a powerful greenhouse gas. The key is sort of what happens once it's in formation. And so we've run core sample tests at the surface to understand, in a way that we can touch and feel what happens when the bio-oil goes into the core sample. And we basically see that it solidifies within 24 to 48 hours without generating gases.
Right, okay.
What's happening is it's repolymerizing. So you've sort of blown the cellulose polymer out of equilibrium, and then but you haven't oxidized it, so then it repolymerizes in one form or another.
Okay, got it. And is there a way of knowing if that's durable over time, or is that something that you just continue to monitor as time goes on?
Yeah, continue to monitor, but from a monitoring perspective, when you have a solid or a liquid underground like that, it's much less of a monitoring concern than compressed CO2, for example, or compressed gas.
Right. Yeah. And in terms of like the well capacity, are there any limits on that when we think about scaling up to, gigatons of removals?
The sequestration capacity is immense. It's hard to overstate how much volume is down there. I think we ran the calculations on like a theoretical class 1 well, and if you have like 100 acres or so at the surface, and then you inject from one well into that, you're looking at like half a gigaton of capacity.
Okay.
So just in the projection of 100 acres, so it's just like vast. I seriously doubt that the wells are going to be a bottleneck anywhere. This is also like a pretty lax, I shouldn't say lax, it's a pretty, there's a lot of formations that are sedimentary in nature that sort of satisfy all the constraints from a safety and long-term permanence perspective. And so you can do this in a lot of places. You're not as constrained as you are with a class 6 well for CO2 injection, where you need a saline dome to ensure that you don't have gas that's escaping out through different holes that might be drilled in, or other ruptures, or so on. So you get a lot more flexibility in location, and there's pretty vast volume per well. We're definitely going to be constrained by biomass availability. That will be the constraint for sure.
Okay, got it. Yeah, and then when thinking about kind of the siting question, I know you were mentioning sort of starting off in Oklahoma. What is the sort of reaction from people, the community, everyone in that area? Are they like excited about it? What are their thoughts on being selected as a storage site?
Yeah, when we went down to Oklahoma for the first injection in January of this year, we were kind of nervous. So there were like 3 San Francisco nerds showing up the day before the Capitol riots in like one of the reddest states in the country.
Yep.
It felt uncomfortable, and the folks though asked, like, what are we working on here? And we eventually explained, like, well, we're working on putting carbon back underground to prevent climate change. And they actually almost welled up, and we're just like so excited to be like in what they perceive to be like the economic future, that they were like, can you send us like stickers for our hard hats? And then now they proudly wear charm stickers on their hard hats. So that was actually a very like formative and interesting kind of moment for us. And I think it kind of shows that how much economic transformation can drive political transformation potentially as well. And it's super interesting. I think there's a lot of potential.
Okay, yeah, great to hear that people have a good reaction with that. We had a question about the cost side of things, and I know you showed that chart showing that you expect the cost to go down pretty significantly over time. Could you explain a little bit more about the drivers behind that and kind of how you expect that to come down so quickly?
Yeah, so there's a few main drivers. So one is the cost of assembly is very high right now, because it's being assembled by the engineers that designed it, which is right for now, but it's not cost effective in the long run. The second is that the machine will get drastically simpler as we build more of them. The third is that the cost of capital is very high because we're venture funded right now, whereas at scale, this will be debt funded. And the fourth is that we expect the machine to last much longer, which all those things amortize the cost down dramatically. Okay.
Makes sense. Another question we had was just thinking about sort of, I know, and with a lot of solutions, there's sometimes a gray area between whether things are avoided emissions or are, actual removals, and thinking about it in terms of the Oxford Principle designations of the different types of emissions or reductions or avoidances. Where would you place your category or your type of removal, and kind of, can you talk a little bit about the distinction between those?
Yeah, so we would consider it a carbon removal, and we would draw the system boundary to include the growth of the biomass. So then you have CO2 coming out of the atmosphere into the biomass getting converted and ending up in the ground. If you draw that, it's a little bit of like a pedantic philosophical point, but if you draw the boundary slightly differently and you draw it such that the biomass is outside of that system diagram, and it would have rotted, then all of a sudden it's an avoidance, right? So depending on how you draw the system diagram, you can classify it either way, but I'm not sure that changes the spirit of what's going on.
Right. Yeah. Cool. We had a couple of questions again about actually geologic storage. So someone asked, what are the type of conditions you need for well storage relatively commonplace throughout the world, or is it going to be a pretty specific set of places in the world where you can do that? And specifically, is it possible to inject bio-oil into non-depleted oil formations?
Sorry, what was the first part of the question? The second part was about non-depleted formations. What was the first part?
Just in general, like, is it quite unique conditions that are required, or is that a pretty commonplace formation?
No, we think it's pretty common right now. I mean, we'll learn more over the coming years as to like what the constraints are, but really the constraints are like staying away from aquifers, getting deep enough that you've got pore space that you're confident is going to stay down there, and then ideally having the pore space be pretty amenable to injection. So like not under super high pressure, right?
Yeah.
But those conditions I think are fairly low bar in terms of it's pretty easy to find that.
That makes sense.
And then in terms of depleted, you theoretically could inject into a non-depleted formation. There might be, for better or worse, there might be legal issues with that around sort of spoiling the formation, as it were. But not sure. We haven't crossed that bridge yet. Got it.
Yeah, we also had a few questions about like, so legally, thinking about the type of bio-oil that you're producing, how does that get classified? Is it classified as hazardous, non-hazardous waste, and how does that affect your ability to find sites for sequestration?
Yeah, it's not hazardous waste. I see the comment here saying that it is, but it's not. Not all bio-oil is produced with a pH of 2. For starters, but yeah, it's not hazardous waste. That would be problematic because then you need very special well classifications. As with many materials, it is sometimes classified depending on exactly the material properties and feedstocks and so on. In different pyrolysis processes, it can sometimes be classified as a hazardous material, which is not the same as a hazardous waste.
Right.
And that creates like needs around its transport and so on. But it really depends on the details of the pyrolysis process as to how it's classified and what that means in terms of how it needs to be handled. Obviously, very safety focused.
Yeah, makes sense. Okay, another question we had was, a couple of people asked actually, how is the process heat for pyrolysis generated and what are the associated emissions and sort of impact on LCA from that?
Yeah, so the pyrolysis uses energy from the biomass to basically drive the process. So we're not connecting up to a utility grid or anything like that. Like we're operating way out in rural areas. So that's why if you look at that LCA again, you'll see there's a huge drop in total amount of sequestered carbon in the pyrolysis process, and that's because some of the biomass energy is being used to drive the heat of pyrolysis. So that means that it's accounted for in the LCA and that's getting re-emitted. That portion would have been re-emitted anyways, but it still counts against our efficiency and total amount of carbon that goes underground. But it means that there's not like a grid hookup or something where we need to account upstream for electricity or problems of additionality where where would that energy have gone, etc. What else could that electrical energy have done? Does it need to be renewable? Those are challenges that like direct air capture in particular has to solve of is the renewable energy additional or whatever, but it doesn't affect our process.
Got it. Another question about the storage concerns. So does it make sense to try to sort of separate out different fractions of the liquid and store them separately, or are there any considerations around that, or does it just make the most sense to store it as a mixed liquid altogether?
I mean, I guess you could, but separation is just like an extra step, so an extra cost, extra OpEx. Okay. I don't know that I'm not aware of a reason to do it, but that doesn't mean there isn't.
Okay, fair enough. All right, and then I just have a couple more. Could you see a similar solution being applied to plastic waste? So converting the waste to oil and then sequestering it, even the process might be a bit different. I guess it could be just a different way to get plastic to its end of life and store it in a safe way. Is that something you would think about?
Yeah, it's possible. There's a lot of other contaminants in plastic that are not in biomass. So I think those would be challenging. In particular, I think chlorine is pretty common in plastics. So we'd have to run some tests and understand what happened. Where does that chlorine evolve? Does it evolve into the gas? Does it evolve into the liquid or the solid? And what does that mean for the sort of downstream and the state of each of those streams? Not clear to me yet. So that would require more study, but it's interesting. Plastic is already pretty permanent. So I also don't know how much additionality there would be there.
Yeah, makes sense. All right, and someone, I think is the last question we'll have, someone asked, any tips on where to start on setting up a bio oil or biochar business?
There's actually pretty deep literature about pyrolysis. There's a lot of research that's happened on it over the last 40 years. So I would probably dig through some of the NREL papers and some of the resources that those folks have put up around all the studies that they've done. That's probably a really good place to start. There's one other question here that I did want to answer, which was just what happens to the nitrogen, phosphorus, and potassium, which is really important. Actually, it comes out in the solid fraction. The vast majority of it comes out in the solid fraction, which is the biochar ash mixture, which goes back on the field. That's an important part of the closed loop on these nutrients to make sure that we're not depleting the field.
Got it. Okay, cool. Well, thanks so much, Peter. That's been super interesting for me. I'll just leave it to Toby to close us out with a couple of comments on next week, but thanks very much.
Thanks for having me. Cheers.
Yep. Thank you so much, Peter. That was really great, and we really appreciate. We know you're super busy, and we really appreciate you spending an hour with us today. It was a very informative and exciting presentation. Just a couple things about what we have coming up. Next week on Tuesday, our regular time, Mega and I will actually be presenting the carbon dioxide removal procurement legislation that OpenAir is developing and answering your questions, and we'd love to get your feedback, so please join us for that. We're going to take the week of Thanksgiving, US Thanksgiving off, and then the 30th, Josh Santos, the CEO at Noya, will be with us to talk about his direct air capture process that is connected to industrial cooling towers. December 7th, we have Sea Change, which was also supported by Stripe, which is a very interesting electrochemical ocean CDR process. It's being developed out at UCLA. Another electrochemical ocean CDR process, Planetary Hydrogen, will talk about their carbon negative hydrogen on December 14th. And then early January, we have a presentation from our very own Chris Neidl and Naeem Merchant about how DAC and concrete together can be a very scalable and high value carbon dioxide removal solution. Thank you again, Peter. We're going to leave the chat up for a few minutes so you can register for next week. There are links to our Twitter, so please follow us on Twitter. And thanks for joining us. Thanks to Peter, and we'll see you next time. The audience for joining us, and thank you for all the great questions. We'll see you next Monday.